In this video, we're going to take a look at working with squares, and these are a couple of factoring patterns. One of them is called a perfect square trinomial, or factoring a perfect square, and I'm going to talk about that over here a bit. And the second one is called the difference of two squares. We'll talk about in the top left corner here, and then show through several examples how you use one or the other to do some factoring. Now, expanding and factoring are opposite operations. So when I multiply x plus 4 or square it, or multiply two x plus 4's together, that's expanding to get these terms. But if you take the end product, the x squared plus 8x plus 16, and factor it, well, that's the factored form, or this is the factored form, this is the expanded form. And just to go over how x plus 4 squared works out to x squared plus 8x plus 16, squared means there's two of these x plus 4's we're multiplying. And so x times x will give you x squared. And then the x times the 4 is this 4x. And then now I've multiplied this x by these two terms, and that's the first two. Now I'll multiply the 4 by each term in the second set of brackets, and I'll get these two. So 4 times x is this 4x. 4 times 4 gives us 16. Now notice that there's two identical 4x's here. So 4x and 4x adds to 8x, and so the expanded form is x squared plus 8x plus 16. Now this, and we don't normally write it in this form, but I'm trying to show the pattern here. So the x squared, I just changed the color. This x that's squared is actually that first term. So whatever is there is squared here. On the end, the 16 is 4 squared. That 4 squared comes from squaring this 4 right here. What's in the middle is two 4x's. Remember there were two 4x's here? Well, the 4x comes from multiplying the first and second term in the binomial. So 4 times x gives you the 4x. We double it because there were two of them. And that's because when you're squaring, there's two identical terms in the middle. And so this is the factoring pattern. When you see a trinomial in this form, it starts with a perfect square and it ends in a perfect square. And the middle term, the 8x, for example, here, is actually 2 times the product of the 4 and the x, okay, what you squared here and what you squared here. Then that would factor into x plus 4 squared. And so this is what it looks like. If you have, let's say, x plus a squared, it's x squared at the beginning, so you're squaring the first term in the binomial. On the end, you're squaring the last term in the binomial. And the middle is 2 times the product of a and x being the two terms in the binomial. So if you have this kind of a trinomial in that pattern, it's going to factor into what's called a perfect square. Both binomials will be the same. So that's a perfect square trinomial, and again, we'll take a look at some examples below. Before we get to that, though, the other factoring pattern is if we're multiplying two binomials together. Now, in this case, the two binomials were the same. Over here, they're almost the same, except one has a plus between the two terms, and the other has a minus between the same two terms. Now, if you expand this out, x times x gives you the x squared, and x times the negative 5 is minus 5x. 5 times x is this 5x, and 5 times negative 5 is negative 25. The 5x and negative 5x in the middle are opposites, so they add to 0. That's why there's no x term here at all. And so it simplifies to x squared minus 25, because they're gone. Now, x squared minus 25 is the same as x squared minus 5 squared. 25 is actually 5 squared. And so the pattern I'm trying to show here is that if you're multiplying two binomials together that are the same except one is a plus and one is a minus between the two terms, it simplifies to just x times x is x squared, and 5 times negative 5 is minus 5 squared. See, the middle two terms always add to 0, because 5 times x is 5x, that's positive, and negative 5 times x is negative 5x. They're opposites, so they add to 0. Now, when you're factoring, if you have something like this, and that's why it's called the difference, notice the subtraction sign, of two perfect squares. X squared is a perfect square, and so would 5 squared be, or 25. And so, this is the factoring pattern for the difference of two squares. If you have x squared minus a squared, it would factor into x plus a times x minus a. Notice what's at the beginning are the same two terms that multiply to give you x squared, What's on the end is the same, well, they're opposites really, because it's a positive a and a negative a that would multiply to minus a squared. And so that's the difference of two squares and how it factors. So in this example, we're asked to factor using the perfect square and or difference of two squares patterns where possible. Remember, sometimes you're given things that aren't possible to be factored. So the first one, x squared minus 12x plus 36. Now notice it's a trinomial. Okay, so it's a trinomial, so maybe the perfect square one works. It starts with a perfect square and ends with a perfect square. So it may factor into a perfect square trinomial. So if it does, and we're gonna try it and then just check to make sure it works. If it does, it would have to be x at the beginning, because x squared is what gives you the x squared. It would have to be a minus here because it's a minus 12x in the middle. And notice there's a perfect square in the end. 36 is a perfect square. It's 6 squared. So if we stick a 6 in here, then maybe this factors into x minus 6 squared. And this is how you check. And actually, I'm just using this pattern here to check. So if you square the x, that gives you that term. If you square the negative 6, it gives you this term, the 36. And the middle term is 2 times the product of the two terms of the binomial. So if you multiply x by negative 6, that's negative 6x. And if you double that, you get negative 12x. So that's really a shortcut, a sort of a mental shortcut. X squared is that, negative 6 squared is that, and this term times this term doubled is negative 12x. So it does check. That would be x minus 6 squared. Second one in B, 16r, it's a trinomial, and 16r squared is a perfect square, and so is the 49. So again, maybe it's a perfect square trinomial. So if it is, it would have to start with a 4r, because it's 4r that you square to give you 16r squared. And on the end we have a 49 here. So what do you square to make 49? And the answer is 7. So they would have to end in a 7. So we'll stick a 7 there, and let's do the check. 4r squared is 16r squared. 7 squared is 49. Now if you multiply 4r by 7, that's 28r. And if you double 28r, you do get 56r. And so it checks. So that's how you can just make sure that it works. Next one in C, 25y squared against a trinomial. 25y squared is a perfect square. And so is 9a squared. See, 3 squared is 9, and of course a, if we square it, gives you a squared. And so this may be a perfect square trinomial. It would have to start with a 5y, because 5y is what you square to make 25y squared. Now, and again, a minus because the middle term's a minus, a negative. And what do you square to make 9a squared? Well, it has to be 3a, so we'll stick a 3a in the middle here. Now, so again, we'll check this. 5y squared gives you this term. Negative 3a squared will give you 9a squared. Now, if you multiply 5y by negative 3a, it would be negative 15ay. So negative 15ay. And if you double that, you do get negative 30ay. So it does check. Okay, next one in D here. Again, it starts with a perfect square, ends with a perfect square. So it would have to be, if it's a perfect square, it's 2x that you square to make 4x squared, and it's 3 that you square to make 9. So we'll put a 3 on the end here, and let's just check. So 2x squared is 4x squared. 3 squared is 9 in the end. Now 2x times 3 would be 6x, and if you double that, you get 12x. So 2x times 3 is 6x. Double that, you get 12x. Well, that's not a 12x in the middle. So this does not factor into 2x plus 3 squared. Now, it may factor, okay, I'll cross this out in a moment here, but if you're doing the whole course here, there's a lesson called factoring ax squared plus bx plus c. So in order to factor this, we would look for two numbers to add to 8. and multiply to 36 because 4 and 9 multiply to 36. So the possible factors of 36, now these are both positive, so we don't have to worry about any negatives here at all, are 1 and 36, 2 and 18 that multiply to 36, 3 and 12, 4 and 9, or 6 and 6. And none of these pairs add to 8. Remember, they add to the coefficient of the linear term. So that adds to 37, 20, 15, 13, and 12. But nothing adds to 8. So this doesn't factor. So we'll cross that out, and you would just say it doesn't factor. Whenever you're using any of the perfect squares, again, make sure you check to make sure that it actually does work. Now in E, here we have just a binomial, and it's the difference of two perfect squares. So x squared is, of course, a perfect square, and it's 8 that you square to make 64, so that's a perfect square. So so this is a difference of two squares, so this is the factoring pattern we'll use here. So it'll be two binomials the same, except that one is a minus and one is a plus. And what goes in the end here are the two numbers that are, well, opposites that multiply to negative 64. So it would be x minus 8 and x plus 8. And again, you can always check this. X times x is x squared. Negative 8 times positive 8 is negative 64. And the reason there's no x term is because if you multiply these together, that's positive 8x, and that's negative 8x, and those add to 0, just like the negative 5x and 5x add to 0 up here. So that would factor into x minus 8 times x plus 8. For f here, again, it's the difference of two perfect squares. 16t squared, they're both perfect squares, and so is 121, that's 11 squared. So if it's the difference of two squares, it'd have to start with a 4t at the beginning, because 4t times 4t is 16t squared. And the square root of 121 is 11, so it'd be plus 11 and minus 11. Now, notice in this case, I put the negative first and the positive second, and here I have the positive first and negative second. It does not matter which one you put first. So just showing that you could change it up a little bit. For g, this is a perfect square. If you take x squared and you square it again, you get x to the 4. So that actually is a perfect square. And so is 16. 16 is also a perfect square. It's 4 squared. And so we would factor this into, it's the difference of two squares. So it would have to be x squared at the beginning, because x squared times x squared gives you x to the 4th. The same two terms. That's why, now the two terms are the same. So you wouldn't put like an x here and an x cubed here. Okay, they have to be the same. Just like, you see, if we're factoring x squared minus a squared, they're both x's here. They're the same two terms that multiply to x squared. So that's why it's x squared at the beginning for both. If this was an x and this was an x cubed, when you expand them out, you couldn't get those middle terms to add to 0. Because if you look up here, for example, if I had an x cubed here and an x here, then this would be a 5x, but this would be a minus 5x cubed, because it would come from multiplying the x cubed by the negative 5. And then they wouldn't add to 0. They wouldn't be opposites. So x squared at the beginning of each. Now, what do you multiply to give you 16? Two numbers are the same, which would be 4. And so we need a plus 4 and a minus 4 here. And so that factors into x squared plus 4 and x squared minus 4. Now, this is the sum of two squares. That doesn't factor. But you see, this is, again, the difference of two perfect squares. This is a perfect square, and so is 4. 4 is 2 squared. So this will actually factor further. This part won't, because it's a sum of two squares. So what we would do is write the x squared plus 4 down, and then this is going to factor into x minus something, x plus something, and the two numbers here are the square roots of 4, which would be, well, negative 2 and positive 2. So there's actually three factors of x to the 4th minus 16, x squared plus 4, x minus 2, and x plus 2. In H, we have back to a trinomial again, so not the difference of two squares. It does start with a perfect square. See, 9 is a perfect square, and so is a squared and b the 4th. See, whenever you have a power of some variable term, as long as the exponent's even, it's going to be a perfect square. Now, 1 is the simplest of all perfect squares because it's 1 squared. So it actually ends in a perfect square as well. So this may be a perfect square, and again, we'll check to make sure it works. So what goes at the beginning is what you square to make 9, so that would have to be a 3. What you square to make a squared, which would have to be an a. And what you square to make b to the 4th, which would be b squared. and plus on the end, and again, the same sign here as here. And what do you square to make 1? Well, it's 1. So we put a 1 in the end there. Again, you can check this. If you square 3ab squared, 3 squared is 9, a squared would be a squared, b squared squared would be b to the fourth. Remember, you multiply the exponents when you have power of a power. 1 squared is 1. Now, if we multiply 1 by 3ab squared, you get 3ab squared. And remember, you double it because there's 2 of them. Remember the factoring pattern here? So 3ab squared doubled would give you 6ab squared. So it does check. Now in I here, this is a perfect 2 terms, binomial again, so maybe the difference of 2 squares. That's a perfect square, and so is that, but you see it's the sum. The sum of 2 squares doesn't factor. Okay, not according to this. Okay, but there is a little bit of factoring you can do here. Don't forget common factoring. Both of these terms do divide evenly by 4, so you can common factor a 4 out. So if you factor a 4 out, 4 goes into 36 9 times, so this would be a 9m squared, and 4 goes into 64 16 times, so we'll put a 16 on the end here. Now this is still the sum of 2 squares. That doesn't further factor, but you can take the common factor of 4 out, and then that's finished. And that's the end of the video.